So we're hopefully starting to get a little bit more comfortable with the idea of mathematical induction. Once again, it's a technique that we use whenever we have infinitely many statements that can be formed and therefore that require proof. I want to reiterate that something like the sum of two even integers is always even can be done without induction. It can also be done with induction, but it's much faster to just do direct proof, because even though we don't know which even number, we always know that an even number is 2 times an integer plus 2 times an integer. We factor out a 2 and we get 2 times the sum of two integers, which is also an integer, and 2 times an integer is an even number. But in situations like summations, we know that that simply can't be done, because depending on what n is, the equation is going to be different. So let's say that we want to add up the first n even integers, beginning at 2 and working our way up, so only the positive even integers. So if we start off again kind of investigating to see, is there a way that I could add up the first n even integers without having to do it by hand? Well, if n is equal to 1, 2 times 1 is just 2, and that's not very interesting. If n is equal to 2, that means we'll have 2 times 1, which is 2, plus 2 times 2, which is 4. That's the first two even integers, which is 6. Now, in our table, we want to, again, start to see a pattern, because right now, just the first two rows, I don't know how these are connected. I don't see any perfect squares. I need to try to establish some sort of relationship between the input. The input is n, and the output is what does the sum come out to be. So here, if I add up the first 3 even integers, 2 plus 4 plus 6, well, that gives me 6 plus 6 is 12. And then if I take the first 4 even integers, which is 2 plus 4 plus 6 plus 8, that's going to be 20. And then we now know that we're just, for n equals 5, we just have to add in one more even integer, which is 10. That gives us 30. And then same thing here. Let's go ahead and say 30 plus the next even integer is 42. So if I just try to see, is there a multiplier that I can apply to n to get the sum? Well, here I'd be like, okay, well, 1 value of n times 2 is 2. But then when n is 2, 2 times 2 is not 6. So that's not the pattern that we're looking for. It looks like, however, that there might be a connection between two sequential n's. For example, 1 times 2 is 2. Let's see if that holds in the next row. 2, the current value of n, times the next value of n. Oh, look at that. 2 times 3 is 6. 3, the current value of n, times 4 gives me 12. 4 times 5 gives me 20. 5 times 6 gives me 30. And then if I had 7 down here, 6 times 7 is 42. Wow, that's pretty cool. So I think that this value, this summation, is simply going to be the current value of n times the next value of n. So n times the next value would be n plus 1. So when n is 7, we're claiming that we should get 7 times 7 plus 1. That's 7 times 8, which is 56. Let's see if that's true. Take 42, add the next even integer, after the 7th even integer, which would be 14. 42 plus 14 is, check it out, it's 56. So we do have a relationship, we have a hypothesis now, that the sum of the first n even integers, positive even integers, is n times n plus 1. Again, a much faster way, if n is like 1,000,000, you want to add together the first 1,000,000 even integers. It's It's going to be a lot of things to add, but we notice that seems to be a faster way. So let's formulate our hypothesis. So think with me. So we just said that if you add up the first n integers, you should get the same result as if you just take n and multiply it by n plus 1. You could also write this, if you'd like, you could write this as n squared plus n. You distribute that through. And that's still true because 30 is 5 squared, which is 25, plus 5 is 30. 6 squared is 36, plus 6 is 42. So all I've done is distributed here. This just might be a little bit easier to work with. So let's go ahead and prove this again by mathematical induction, because there are infinitely many equations that are going to come out of this. And we first have to prove our base case. Well, what's our base case? What's our smallest value of n? Well, it's 1. It can't go any lower than 1 because you can't sum from the first odd integer to the 0th odd integer. That doesn't make any sense. Even integer. So prove p of 1. i.e., what do we want to prove? We want to prove that does the sum from I equals 1 to 1 of 2i, in other words, just the first even integer, is that the same thing as taking 1 squared plus 1? Or you could use 1 times 1 plus 1. Well, we've already done that. We already did that in the table. That's the nice part. Question mark. Sum of just the first even integer is 2. 1 squared plus 1 is not 3, is 2. And that checks out. Those two things are equal to each other. Next, I'm going to assume p of k. In other words, that the sum from I equals 1 to k, in other words, the first k even integers, should be k squared plus k, right? Because whatever this is, that's the same number as this and the same number as this. So if we sum to k, we should just be able to replace our n's with k's. So assume that's true. That's all we need to do there. But we still have the burden of proof to establish for p of k plus 1. In other words, assuming there's a domino that can be tipped over, the kth one, will it knock over the next one? Because if it does, and we know that p of 1 can be tipped over, that's going to tip over p of 2, which will tip over p of 3, and so on. Okay, so we need to prove that the sum, think with me here, from I equals 1, the first even integer, positive integer, to the k plus 1th even integer, and the even integer is of the form 2i, should be what? Well, it should be the k plus 1th integers, or k plus 1 squared, whatever we're summing to is what gets squared and gets added. So it should be k plus 1 squared plus the value of that n, which is just k plus 1. Okay, so that's what we need to prove, i.e. prove this. We don't know that it's true yet, but we want to see whether or not it is. Do we end up getting k plus 1 squared plus k plus 1? Well, again, one way to do this is to set up the sum. I mean, we're always going to start with, well, let's see what the sum turns out to be and see if it agrees with what we expect. This is just what we expect. What we expect to get if p of k plus 1 is true. All right. Or you could alternatively write, you could say, well, k plus 1 squared, you could FOIL that, plus k plus 1 will give us k squared plus 1, 2k there, 1k there, it's 3k plus 1 would give us plus 2. So that's just another form. Rather than having to factor, sometimes it's easier just to distribute. And then we could say, well, we expect to get k squared plus 3k plus 2. Well, how do we proceed from here? The first thing we need to think about is, what does this mean? Well, this means I'm going to add 2 plus 4 plus dot 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 up to the kth integer, even integer. And the reason I want to do that is because I want to use this formula. I want to be able to say that, hey, we already know that the sum of the first k even integers is k squared plus k. So this will go all the way up to 2 times k. Once again, what that represents is that is the kth integer. But now we need to add on the next even integer, because we're adding up not just the k integers, even integers, but the k plus 1 even integer. Well, that would just be 2 times the value of k plus 1. And as before, that represents the k plus 1th, sounds funny, even integer. Okay, so this is that's really the key in working with these summations. It doesn't really matter what the summation involves. In this inductive step, you want to break up your sum into a component that represents your p of k, and then to acknowledge how that last term will allow you to get what you're expecting. Now, if it's a false statement, you're not going to get what you're expecting. So that's why we form a hypothesis first. If we ever fail at this step, A, we could have made a mistake in our algebra, or B, the statement is really not true, and you will not get what you expect if it's a false statement. I'll show you an example of that in a moment. Okay, so when we collect the first k, the sum of the first k even integers, well, we already know that that right there is sum from I equals 1 to k of 2 i's, which is equal to k squared plus k. Okay, so that equals that whole underlined, underbracketed expression can be reduced to k squared plus k from our assumption step. And then we have this extra plus 2k plus 1. Now, let's combine like terms and see if we get k squared plus 3k plus 2. Well, that's k squared plus k, distribute, plus 2k plus 2, and oh goodness, there it is. 1k plus 2k is 3k plus 2, and that is exactly what we expected right here. We got exactly what we expected. So the inductive step is true, and so we want to just conclude. We need a conclusion. Can't just leave it there. We're concluding that the sum of any n even integers beginning at 2 is equal to n squared plus n, or n times n plus 1 if you prefer. And we are done with the proof. And we only had to do 3 things in order to prove infinitely many cases. It's really cool. Now, just to show you really briefly that things won't work out if the claim is false, let me craft an example here for you. Let's just say that I want to add up the first n integers, positive integers beginning at 1. So 1 plus 2 plus 3 plus 4. So not skipping evens, not skipping odds, all of the integers beginning at 1 and ending at n. So the way I'm going to write that is the summation from I equals 1 to n of what? Well, it's just the value of I. When I is 1, you get 1. When I is 2, you get 2. When I is 3, you get 3. We're not just counting in evens, and we're not just counting odds. We're counting everything along the way. So let's just say, I'm going to make something up here. Let's just say that we believe this to be n squared. And we didn't build a table, but somebody told us this, and we're like, okay, let's roll with it. So this says the sum of first n positive integers, not just even, not just odd, is n squared. And let's say we go about our business and we're like, okay, let's just prove it. If you say it's true, let's see how the proof pans out. And if we did this for the first case, which again, n can be as small as 1. So for the base case, we want to prove p of 1. Let's see if that works out. To prove p of 1, we want to show, i.e., does the sum of the first to the first integer equal n squared? Well, the sum of just the first integer, that's just 1, so that's equal to 1, nothing to add with there. And, question mark, does that equal 1 squared? Well, check it out, 1 equals 1, and so all is good in the world. So if we stop there, then we would be in trouble, because this formula is not going to work. And you might think that, well, because you assume p of k, that might be an error in logic. But remember, there's still a burden of proof on us. And so let's just go through the motions. So assume p of k, i.e. assume that it is true that the sum of the first k integers is equal to k squared. Then we need to now prove the induction step, p of k plus 1. Well, what would we expect if our formula was true? We would expect that the sum of the first k plus 1 integers would be the square of k plus 1. And that's the same thing if you want to FOIL it out. K squared plus 2k plus 1. Well, let me give you a little tip here. This looks a lot like the sum of the first odd integers. Yeah, look at that. That actually gives us the sum of the first n odd integers, k squared plus 2k plus 1, right? That's n squared was what we got when we summed up only the odd integers, 1, 3, 5, etc. So we already know that this can't be right. But let's just go ahead and see what the mathematics shows us. So this is what we would expect to get. So what are we going to do? Well, we are going to start off by formulating that sum. And we're going to write that as, well, the first integer plus the second integer plus all the way up to that kth integer plus one more, plus k plus 1. That's our k plus 1th integer. And we know that the collection of these first k terms, by our assumption, is equal to k squared. Now, onto that, we have this extra plus k plus 1 term. And it doesn't matter how close you are, if it's not exactly what you expect, it's not right. That equals k squared plus 1k plus 1, which is not what we expected. What we expected was to get k squared plus 2k plus 1, but we got k squared plus 1k plus 1. We didn't make any mistakes. In the algebra, whoever had given us this claim gave us a false claim. So this right here is a false claim. And that's how the method of induction will pick those up.